Dear students, today we are starting with a new lesson, Limits, which is the 7th lesson of part 2. Chapter 7, Limits. Students, limits are associated with functions, so let us recall the definition of function and an example. A function or mapping f from set A to set B is represented by this f from A to B is a relation which associates for each element x in A there exists a unique or exactly one element y in B. We have already learned the relations from a set to another set. So, to become a relation to become a function, there exists a unique element in the set B. Then the element y is expressed as y is equal to f of x and is said to be a function in x. We represent the straight line equations y is equal to ax plus b. It is y is equal to f of x. It's a function in x. Here we say y is the image of x under f. F is also called a map or transformation. If such a function exists, then A is called the domain of F and B is called the codomain of F. Let's see an example with an arrow diagram. Here sets A and B are given. Venn diagram is drawn with arrows from A to B. Means there exists a relation from A to B. We have A is associated with the element 3 in B. B is associated with 3, C is associated with 4 and D is associated with 2. That is, for each element, each and every element has images in B. And there is only one image in B. A has only one image, B has only one image. It can be same but there is only one. And C also have the element 4 in B. D has the element 2 in B. So, each element in A has image in B. So, every element from A is associated to exactly one element in B. We have R1 is a well-defined function. Okay. Students, before starting to learn the lesson limits, you have to learn the lesson functions thoroughly. Now, we will start with the lesson limits. Limits is a fundamental concept in calculus and calculus is an important branch of mathematics. Now, let us go through the important points in limits. Meaning of x tends to a, where x is a variable and a is a constant. If x takes values closer and closer or nearer and nearer to a but not equal to a, then we say that x tends to a. It is represented by x with an arrow towards a, x to a or x tends to a. Now there are two cases, that is a is a constant. If we mark a point on the number line, towards left and towards right, there are so many points on the number line from A. So, if x takes values from left of A, then we say that x tends to A minus. A minus, it is written by A raised to minus. The meaning is x is taking the values from left of A and it reaches to A. And if x takes values from right of A, then we say that x tends to A plus, means x is approaching A from right, or x takes the values which is right to A. Let's see an example. Consider the function f of x is equal to x plus 3 and consider the case, take the value of x very close to 3 but not equal to 3, means x is approaching 3. X approaches to 3 from left, means the value of x increases to 3. That is 2.5, 2.6, etc., etc., 2.99, etc. Still it is not very near to A. Again we have so many unlimited number of or infinitely many number of decimal places before 3. And corresponding f of x value will be, by substituting this 2.5 in this function, you will get 2.5 plus 3, 5.5. Similarly, corresponding f of x values are 5.6, 5.9, 5.99, etc. Now this is the case from left. Now x approaches to 3 from right. That means from a bigger value x is reaching to 3, that is decreases to 3, and corresponding f of x values. X is 3.6, 3.5, 3.4, 3.2, etc., etc., 3.1, 3.01, etc., etc. Last, if the x is still limiting value, that will be what? 3. And at the same time, f of x value will be 3.6 plus 3, that is 6.6, and 6.5, etc., 6.1 and 6.01, etc. That means the above table shows that x gets nearer to 3, the corresponding values of f of x gets nearer to 6. Now let's learn the definition of limit. Let f of x be any function in x, then any change in the value of x makes corresponding change in the function f of x, because f of x is written in terms of x. So when we substitute the value of x, we will get another value for f of x. Now if x takes values closer and closer to a, then f of x takes values closer and closer to a constant value, say L. Then we say that the limit of the function f of x is L when x tends to a, or when x tends to a, f of x tends to L. We can write it as LIM, we read it as limit. When x tends to a, f of x is equal to L. You have to be careful while writing this symbolically. That is limit. Under this you have to write x tends to a, and in the main part f of x is equal to L. Now there are two cases. We know x tends to a from left as well as from right. So left hand limit is limit of the function f of x when x tends to a minus, that is a, x takes values from left of a, and it is represented by limit x tends to a minus f of x. And right hand what will be right hand limit? That is x takes values from right of a, is limit of the function f of x when x tends to a plus is called a right hand limit. That is limit x tends to a plus f of x. Now these both, that is limit x tends to a minus f of x, that is left hand limit, and right hand limit exists, then each one is called what? One-sided limit. Before going to learn the evaluation of limits, let's understand certain important points. First one, if p of x is a polynomial in x, then the limit of p of x when x tends to a is equal to p of a. Means in this case we are obtaining the limit of p of x by the direct substitution of x is equal to a. Second one, rational function. What is a rational function? The function of the form f of x equal to p of x upon q of x, where p of x and q of x are polynomials in x. In this lesson, we are going to study the limit of a rational function. F of x is equal to p of x upon q of x as x tends to a, where p of x and q of x are polynomials in x. Now, when we consider this rational function, there are three cases. In the denominator, there is q of x. So, when we substitute x is equal to a, it can be first one, q of a may not be 0, that is not equal to 0 case can occur. Or the second one, q of a equal to 0 and p of a equal to 0 also possible. And the third one, q of a equal to 0 and p of a not equal to 0. So there are these three different cases when we consider this rational function and substituting x is equal to a to evaluate the limit. Let's analyze the three cases. Case 1, q of a not equal to 0. That is, say after substituting x equal to a, then if the denominator is not equal to 0, then the direct substitution of a, x is equal to a, gives the value of the limit. That is, limit x tends to a, p of x upon q of x is equal to p of a upon q of a. Now the second case, if q of a equal to 0 and p of a equal to 0, that is both numerator and denominator is equal to 0 after the substitution of x is equal to a. In this case, we know that if q of a equal to 0, x minus a will be a factor of q of x. Similarly, p of a equal to 0 means x minus a is the factor of p of x also. Then we will express p of x and q of x all as x minus a into some p1x and q of x is equal to x minus a into some q1 of x. That is, we can factorize this polynomial with one factor is x minus a and the other factor, that is p1x and q1x. Now then we will write p of x upon q of x is equal to x minus a raised to r p1x, because we don't know how many factors are coming like this x minus a form. So we will just write the exponent r or power r here, and x minus a raised to s q1x, where x minus a is not equal to 0. Now here also we have three cases. If r is equal to s, what will happen? If r is equal to s, for example, r and s are 2, then x minus a whole square, denominator also containing x minus a the whole square, then both will get cancelled. In that case, we will get what? Limit x tends to a, p of x upon q of x is equal to p1a upon q1a. Now, the second case is r greater than s. Then we can cancel the factor x minus a whole raised to s from both the denominator and numerator, and some term will remain in the numerator, that is in the form of x minus a. Then limit x tends to a, p of x upon q of x is equal to 0, because when we directly substitute x equal to a, this factor, remaining factor in the numerator will be a minus a, so it will be 0. And the third case, if r less than s means the term, that is x minus a raised to r, will get cancelled from both numerator and denominator, and the denominator containing the remaining factor with x minus a raised to some other number. So there if we directly substitute, the denominator q of a will be 0 here. That is, x minus a means a minus a when we put x is equal to a. Then we have to proceed to the case 3. What is that? Q of a equal to 0 and p of a not equal to 0. In this case, as the denominator is becoming 0 when we substitute x equal to 0, we see that limit x tends to a, p of x upon q of x does not exist. Clear? Remaining part of the lesson will be continued in the next video. Thank you.